have a little handout. I'm not going to have a quiz over or anything like that. Kind of sleep, eat, just kind of relax for now.
We need to resolve the LP.
Let's
Our program right there.
And we'll get started in just a second. There's a research interest I have. It's called data development analysis. And notice the slide doesn't say anything about data development analysis. That's because DEA, data development analysis, is a lot more. And on top of that, we have a relatively varied group of people here. And I was trying to see if I could do this and not bore everybody and kind of hit a little spot of interest for various people. So let me provide this handout to you guys. We got one more there. And this is the last one. But anyway, data development analysis involves LP, that's linear programming, Excel, and it's applied to merit evaluations. At least it's being proposed by me, or has been, I should say, to be applied to the faculty evaluation process. So it reminded me of lions and tigers and bears. Oh no. That's why my apologies to Frank Baum, because even though Frank Baum did not come up with that expression, it's part of the screenwriter's stuff in one of the Wizard of Oz movies. Yeah, you know all about that. Wizard of Oz movies. Anyway, I just thought about that. So I thought maybe it would be helpful to have a little slide here that at least refers to Dorothy and the Wizard of Oz. Maybe get a little chunk out of that. So we're not talking about going back to Kansas. We're basically dealing with three things that, again, as I said, reminded me of the expression lions and tigers and bears and whatnot. But anyway, the problem. Of course, you don't want to develop tools without having the problems that have been solved. So that's basically the problem with races. Merit evaluations are a real pain. For anyone who's done it or been evaluated, it's not pleasant. And students don't like being evaluated with respect to their grades. And they'll say, well, I really did well in this thing, but it didn't count as much as that thing. Well, basically, faculty evaluations are the same. I really did well here, but I didn't get counted as much because, that counted more. Or you just took all the stuff and averaged it together. I put down that essentially every faculty member is good at something, or at least relatively good at something. That means compared to, how he or she does on others and compared to other people. And there needs to be a way that we can get away from someone saying, well, this area is worth this much and this area is worth that much, because to different people, these different areas have different worths or weights. So the concept of Pareto efficiency is being, or was used when Charnes, Cooper, and Rhodes developed the concept of data development analysis. They went back to, I forgot, not about 1956 reference, dealing with the efficient frontier. The idea is use a tool, data development analysis, to develop or identify the efficient set of faculty members. Efficient being the concept of economic efficiency, where you don't see anyone getting better. Basically, you can't find anyone better on a given point without finding worse on a different attribute. And we'll look at that graphically. It's a little more interesting as well as meaningful there. We basically avoid answering which area is more important. We can use linear programming with some help from Excel. Linear programming is a mathematical modeling tool. Excel, of course, is just a spreadsheet, but Excel has various algorithms that have been built into it, and you can basically basically use linear programming solution algorithms to a model that we will build in Excel. Hence, Excel, LP, and Merit, or LP, Excel, and Merit. Oops, that wasn't supposed to be that way. Consider what I give you on the handout. Small, fictitious, obviously, lumber company, very simplified case, where we have a company that is concerned about three products. They make more, but we're looking at three products right now, plywood products. CDX, which is grade C, grade D on the one side and the other, exterior glue. AC plywood, which is A grade on one side, C on the next. And form plywood. These are all real grades of plywood. And given what you see in the case description, profit per panel for CDX plywood is $5, profit per 4x8 sheet for AC plywood is $7, and profit for form plywood is $6. Initially, a person would be inclined to make all AC plywood because that's where you get the most profit. But there are some restrictions, some limitations on the resources that are used to make these things. Now we're assuming here, unrealistically, but we're assuming that there's unlimited demand, that basically whatever we can produce, we can sell. That's not a problem. We can always build that into the model, but I didn't want to make a model more complex than this to start with. And besides that, the point is not solving the livest lumber production planning process problem, but basically looking at the tool in a simple fashion so we can apply it to a more complex problem of the development concept. The linear programming model for this pretty much takes this information and applies basically flash. There's some pizza here if you want to grab some. Okay. Basically, the linear programming model will simply say, okay, we're defining some variables, that those variables are what we are trying to do, what we're trying to accomplish, and then based upon that, we have mathematical expressions that relate these variables and our resources and so on. So if we look at the LP model, we see that we can set up our variables, our decision variables, and I apologize for the subscripts for those who are bothered by subscripts, but just think in terms of X, Y, and Z if you want. But anyway, one thing we want to do is determine the number of sheets CDX produce. Another thing is to determine the number of AC plywood to produce, and X3, the number of sheets of AC plywood. I think actually what it is, I think it's mixed up. Don't, on my definition, I think AC is actually X2, but anyway. We can fix that easily. The objective then, given these variables, given the problem statement, is to maximize 5 as profit for one item, plus 7 times the profit for the other item, plus 6 the profit for the other item, times the amounts produced. So the weekly profit based upon production of these 3 different kinds of products. Subject to, that is limited to, ST subject to, limited to the fact that the amount that we spend in the cutting area is no more than 54,000 minutes a week. The amount that is taken up in the gluing area is no more than 24,000 minutes a week. And the amount that's spent in the finishing area is no more than 36,000 minutes. So we basically take those numbers that you saw on the table and basically apply them, essentially multiply them times the corresponding amounts of each of the products we are considering making. So I put down here, it's simply a matter of determining what's the best combination of X1, X2, and X3. Pretty easy, right? Well, we can try 1,000 sheets of each. No, that won't work because we overshoot our availability. Let's try 10 sheets of each. No, that's not going to use up all the available resources. Well, let's try 10, 150. Well, we can basically have an infinite set of possible values, or essentially an infinite set of possible combinations of X1, X2, and X3. And that's where, let's see what I've got here. The Excel model comes in, or for that matter, any sort of computerized solution process, or before that, the basic simplex algorithm, which basically goes through this matrix of numbers and step by step ultimately arrives at what is going to be the best combination of X1, X2, and X3. But anyway, Excel model is easiest for us to deal with, and besides that, we can build some additional capability into Excel, macro capability that makes it more than simply a table of data, more than simply a bunch of formulas, more than simply a single solver algorithm. We can basically move beyond that. Okay, enter Excel. We're going to create a spreadsheet table. Well, I did create a spreadsheet table that looks like the summary table. We're going to add a few formulas: profit, amount, resource consumed, and solved by trial and error. Well, that's one thing, but a better way to do that is use Excel Solver built into Excel. And that way we can not have to go by trial and error, different values of X1, X2, and X3 over and over and over again. We can basically simply click on a button. It tells us the best values of X1, X2, and X3 after we have told it what we're trying to accomplish. And we can also tinker with the parameters. That is, suppose we don't get $5 profit. We actually get $5.50 profit. Does that change our decision? And so on and so forth. So we can do post-optimality analysis very easily using Excel, more easily than you can typically in other commercial or commercial-based math programming software. Okay, even better is to use Solver with the macro button, which we'll take a quick look at. And I indicated we could call it subroutine when we call it subroutine when editing. All right. We could, I was going to go into this, I won't, but anyway, we could automatically record the steps involved in the macro, and then we basically assign it to a subroutine, and then when we assign a macro to the button, we can actually say, call it the subroutine, but we'll not do that at this point. But let me just get out of the abstract mode and address the initial data. Got that? It's the table you've got in the handout. And by the way, the flip side of the handout shows some of this. That is basically to show the Excel model as well as the mathematical, math programming model, which we saw. Let's see. So I did just a little bit more than what was in the table. Again, the original table is like what you have. It's right here. That's what's available. These are the profit and the coefficients regarding how much time is used in each of the areas. And note the big question is, how much should we make a CDX, AC, and form plywood? Going over here, I did a little color coding. That's not the major point here, but we're doing the color coding just for your information. Green, I indicate on a spreadsheet as those things that are, just go ahead and play with it. Don't change those values all you want. You're not going to hurt anything. And typically what you're trying to do is find out good values to go where it's green. So green for go. Yellow, change those things with caution. Don't mess around with those unless you know what you're doing and really are trying to see what's going to happen if, let's say, it takes 20 minutes for form plywood to go through the cutting area. And then you can change it. But anyway, yellow change with caution. And then that's kind of red. But I didn't want to use real red because you wouldn't be able to see the font behind that. So it's a pinkish thing. Red basically means don't mess with it. Don't change that. Red is wherever I have a built-in formula. And just for your information, the built-in formula here is calculate how much total profit will occur. That is, our total profit is equal to how much CDX times $5 plus how much AC times $7 plus how much form times $6. And basically that sum product says take this vector of B2 to D2 multiplies times this vector of B3 to D3.
So that corresponds to that profit function you showed on the previous
That's
slide.
right. That's what we're trying to maximize. So that if we say maximize something, and in fact in just a second you'll see that we're going to tell it to maximize that cell. And again, we're not maximizing a cell, we're essentially maximizing the results of the count formula that's in that cell. Now, interestingly, it's the same formula I use in the next cell. So I just entered that formula once. That's the nice thing about Excel. You can put together in a logical fashion and oftentimes just copy your formulas down from one to the next to the next. So it saves some of the grief you might have if you're actually trying to enter a formula and basically didn't know better and tried to enter formulas to use. Anyway, I created formulas that indicated the results. So for a given set of values we put in the green area, our results are so much profit and we will use up so much time in the cutting, gluing, and finishing area. Then I said, okay, do I have Solver on here? Tools, Solver. Okay, let's go ahead and tell it here that I want to do something with this target cell. That's the objective cell. So I'm going to set that cell to be equal to results for profit. And then I want to tell it, and it always says maximize yield. I want to maximize that value. And I want to change values that are in these cells, the green cells, and I can specify each constraint. That is, the value in this cell must be no more than the value in this cell, and so on and so forth. Or I can simply specify very easily a constraint that says these values right here must be no more than or equal to the values in those cells. So I'm basically able to commit such a vector here compared to the vector there, item by item. Those values are compared to that cell. Okay. Now I need to do something else, and that specifies some options. I need to tell it that this is a linear model, and values for the green items cannot be less than 0. They have to be something positive. Keep a positive outlook, right? So you've got to keep your positive outlook on production. Not really. So I basically got an Excel model here. That is, I have a spreadsheet with numbers and formulas in it. And then I have behind that for that spreadsheet, for this particular sheet, I have something that tells Excel when you go through the process, try to maximize that cell, change these cells in order to do it, and make sure you adhere to these requirements and any other options I specify. Click on Solve. And this is the screen I want to get. It says found a solution, everything's optimal, so on and so forth. And I'm going to save the solution. And as you can see, the best course of action is to produce 1,200 sheets of CDX plywood, 4,800 sheets of form plywood. Now remember, the good way of doing this initially is simply to try different values of in there, like 100 here and 1,000. Oops. And see what happens, trial and error. But that was a kind of good way, because at least it was all built into the spreadsheet that performance. But the better way is to use the solver. And what I would consider a best way is to put a little button on there. Add a button, and if we do that, would be going back here. Just go Tool, no View, Toolbars, Control Toolbox. Just like in Visual Basic, click on that button there, draw a button. Give it a few properties, and also tell it what to do. In this case, all I need to do is tell it solve or solve. And in fact, let me just show you the results. I'm going to cancel out of this. If I should have done go into design mode, click on this. You can see all I had to do was tell it solve or solve. Now you have to look this up. You have to basically be familiar with Excel's objects that are available to it and so on. But anyway, I call the solve or solve, and then say basically when and then I say when done, basically close it out. That's a thing you have to do. Otherwise, it says at the very end, leaves everything up there. Do you want to keep the current solution? Then there's one other thing that needs to be done. So basically, right on the subroutine that corresponds to the button, so basically double-click the button when it's in design mode. In that subroutine, write that line. And then I would also go up here to Tools, References, and I would make sure that I've got this solver reference, which basically relates what's in this Excel workbook to what's in the file called solver.xla, which is a set of macros and related, well, set of Visual Basic functions and objects say, that can interface with Excel solver. Anyway, that's enough on that. If I go, let's take it out of design mode. Okay, design mode. If I go here and just click on solve, it does that. Now, if I've already solved it, there's no reason to mess around with the macro button. But suppose I decide that, well, 550 is what I'm getting for that sheet, so let's put in 5.5 here, and I can, oops, 5.5. That's a good profit, no question on this. That shows there. Click on solve, and it basically recalculates there. It says, yeah, your profit goes up, but still want to produce the same amount of CDX and foreign violence. Let's suppose I go up to $8 here. Solve it again. Said, oh yeah, there you want to produce nothing but CDX violence. So you can do some trial and error stuff, post-optimality analysis, much more easily if you have some sort of a little solver button or macro button built in. Chris.
John, you might want to tell the students that they haven't used the solver option. If it does not appear on their toolbar, then all they've got to do is go down to add-ins. Right? They can go to add-ins, and then there should be a little box that comes up, and just check the solver option. And from that point forward, it should appear on your toolbar. Okay? If you want to go home and try to duplicate the results.
Yeah. Should you be inclined, solver's got some really neat stuff in it. It really can do a lot of nifty things, and that's I think one of the benefits out of a management science class or a managerial econ class, where you actually can start familiarizing yourself with some powerful tools that are built into Excel. But yeah, by default, when you install Excel, it doesn't have the solver choice available. So you basically, wow, what's going on? Well, click on add-ins, and it brings up this box of stuff, such as analysis toolpath, solver, solver, add-in, and other stuff that you can basically interface with Excel. Stuff that's essentially routines that are written to work with Excel. Thanks. Okay, so that's LP. Also, look at the Excel aspect, that is using Excel to help us with the linear programming solution process. So we can take a problem, the information from the problem, put it in sort of a tabular fashion in an Excel worksheet, and then oftentimes build some formulas in that basically interrelate that stuff, and then use solver to come up with a solution with what we need for whatever our decision problem is. Now, taking that and applying it to the merit problem, we typically, as faculty, are evaluated on 3 areas: how well we teach, how much research and how well we do research, and the service we perform. Rather than getting into the whole picture, I wanted to look simply at the teaching criteria. Our College of Business evaluations have 35 little things, 35 little different dimensions that we're supposed to be evaluated on. That's a pain in itself, but not getting into that. All too often we simply look at the average across all 35 as opposed to simply looking at each one. This person did great as far as prepared for class, got 4.99 on that. But basically, as far as how clearly she explained, it was only at a 3.85. And instead of looking at the individual ones, we typically look at the average. We add them all up and divide by 35, and that's what we have. Essentially what that does is we basically have things like follow syllabus as equally importantly weighted as explains clearly. And I think most people would not agree that following the syllabus is anywhere near as important as explaining a topic clearly. But it's equally weighted. So that's one of the flaws we have to deal with. Now, table 1. If I can find the mouse pointer. There we go. Table 1 shows pretty much what we used to have for the Economics and Decision Sciences Department for evaluations. And I went through this set because it's a little easier to handle than our 35 question evaluation we have now, and it works better for demonstration. We have one criterion: impartial, another prepared for class, another punctual, another available, articulate. These things, there are 8 criteria along which we were evaluating, 8 dimensions, if you want to call them. And an example score might be 2.17. That is, all the students' values added up for that, what they say for you on that one adds up and divided by the number of students gives 2.17 on the instructors available to help students outside the class. That instructor is probably not very available. While this is based upon what we used to have in the College of Business, the numbers are fictitious. There might be people who have scored that well. I think that's mine, probably. But anyway, these are truly fictitious. They were randomly generated to basically prove a point. Provide a demonstration. They do prove a point.
Did you use Excel's random number generator for that? Or?
Yeah, I did actually. But I provided a distribution to work. Anyway, a small example, a couple small in college business. We aggregate the results. That is, add them all together. I mean, for example, add all 8 scores on all 8 and divide by 8. Essentially, as I said, are coming up with a number that is saying all are equally important. But people typically want a single number. They want to know, how did you rate with your teaching evaluations? Well, I got 4.57. Okay. That doesn't provide much information, but it's oftentimes all people want. But again, it hides some information that's important. Typical scheme is, as I said, the simple average. And table 2, if we have, like, I'm not sure, I think there were 20 faculty members I generated for this, and there were 8 criteria. And so basically, since averaging 3.78 was one instructor, 3.88 is another, 2.43. Those are weighted, no, those are non-weighted averages. Or I guess you could say they're weighted average where each value, with each result was weighted by 1/8. The weighted average will get beyond that. Instead of equal weights for every item, we can basically have one weighted more than the other. So, for example, the syllabus might be weighted only, like instead of an equal amount, 0.125, it might be rated as 0.05. Whereas explains things clearly might be rated at like 0.2, and so on. We can have some say in what's important. The trouble is, nobody agrees on what's important. And management by objectives is a way of getting around that, MBO, but that has its faults too. People tend to work strictly toward what they've written on their MBO scheme and ignore the other stuff. And so it produces some essentially perverse results. So what's wrong with the simple average? As I said, it obscures individual strengths, it's artificial, it values minor differences. DEA to the rescue, data and development analysis. And I put a question mark there. Is it or is it not? Is it just adding more complexity and making things more confusing? Well, it has to be determined, but at least let's look at it. We want to evaluate the behaviors, that is the decisions, on a basis of multiple criteria. So we have multiple things to look at, and we don't know how much each of those things is worth. We can say, okay, ahead of time, yeah, this is worth that, and this is worth that, and so on. But DEA avoids that, because what it does is find out those people who are considered to be the efficient group. That is, those people who may not be the best in everything, but basically are best in or do well in a particular category, and you can't find someone else with a better essential combination of results. And that's going to typically be several people. What we're going to do is consider each instructor to be a decision-making unit. DMU is the terminology you'll see in data and development analysis. And so they use that term. So each instructor is a decision-making unit. We apply the concept of economic efficiency.